Hello there, my name is Reveni Sanin Ananaha from University Technology Mara, UiTM Shah Alam, Malaysia, and I am your presenter for today. For today's presentation, titled Modeling RTK-GNSS Trajectory Data Using Sparse Gaussian Process Model. For this presentation, it will include the introduction, problem statement, objective, methodology, result and discussion, and lastly, conclusion. Firstly, for the introduction, researchers from reference 1 and reference 2 mentioned that the development of real-time kinematic (RTK) and global navigation satellite system (GNSS) resulted in various RTK-GNSS devices to enhance the positioning accuracy that provide centimeter positioning. Various research work has been conducted to model and improve measurement error of GNSS based on the Gaussian process regression, also known as GPR, which is a type of kernel machine that could be trained with a given training data set. The trained GPR is a specific by mean and a kernel function serve as a Bayesian non-parametric prediction model. The trained GPR model is useful to process positioning error for GNSS. In reference 5 and reference 6, the researchers have utilized GPR to model error in a static GNSS station. GPR was trained to detect a transient strain resulting from slow slip event in the Pacific Northwest. Maximum likelihood method was used to determine the parameter that need to constrain in the covariance function. Next, the GP model was trained to predict the vertical total electron content, also known as VTEC value, for any geographic coordinate to eliminate the signal delay as mentioned in reference 5. In reference 6, the GPR with a reduced computational complexity was trained to estimate the transient strain from GNSS data from static data station. GPR was used to describe a local trajectory model using spatio-temporal dataset as mentioned in the reference 4, 7 until 9. GPR has been applied to estimate the GPS positioning variance along the bus trajectory by the mean of the mixture of a GPR trained using the GNSS position and timestamp data. A mixture of GPR was trained with a timestamp and a speed information of the buses were used to predict the time arrival for a public transport buses as mentioned in the reference 4. GPR are used to recognize common activity from spatial datasheet as mentioned in the reference 7. And lastly, for the introduction, researchers from reference 8 and 50 mentioned that sparse GPR was utilized to perform trajectory modeling. Next, we move to the problem statement. Researchers from reference 8 and 15 mentioned that the method to develop Gaussian process, also known as GP model, for dynamic measurement of GNSS with the most effective kernel function and parameter was not indicated. The performance of GP model fit on data of the trajectory was not studied. There is a need to further synchronize the residual of GP model for unmodeled error that may reflect on the quality of the model fit. As we can see for the reference 10, state that the unmodeled error are systematic variation that can be detected in the residual of mathematical model which difficult to be further modeled by setting up the additional parameters. Researchers from reference 5 and 6 mentioned that training the conventional GP may be tedious and time-consuming. The sparse GPR model may reduce the computational and memory complexity of a conventional GPR via approximating the posterior GP with a set pseudo-training, also known as inducing point or inducing input. This provides a faster training time and better control over computational complexity. Move on. There is two objectives that we need to achieve. Firstly, to develop sparse GPR model with the most effective covariance function. Secondly, to evaluate GPR model fit on the trajectory data to reveal the unmodeled characteristic.
Next, we move to the methodology. Figure 1 shows the RTK-GNSS used in this work, namely Emily-Rich RS. This GNSS receiver can receive signal from GPS, Galileo, GLONASS, BEDAO, SBAS, and QGZSS satellite system. The communication with the Emily-Rich RS can be established via Bluetooth or Wi-Fi using RichView app. The RichView apps enable configurations of an Emily-Rich RS via the smartphone. For Figure 2, we use two sets of Emily-Rich RS. One is rover, that attached on the top of the car, and another is a base station. The base station sends the correction continuously to the rover via LoRa radio frequency, and rover will identify its locations. Figure 3 shows the red path indicate the trajectory traveled by the rover. Meanwhile, the X mark has been placed on a football field as a base station. The baseline from the base station range from 200 to 500 meters. The data logging of dynamic measurement was conducted during clear weather and clear sky condition. 3 datasets were collected for this trajectory. Next, a georeference map was developed for this location using Quantum Geographic Information System, also known as QGIS software desktop version 3.16.2, as we can see on the figure 4. 14 georeference points were collected using the RTK-GNSS to produce a georeference map. An actual ground truth trajectory was subsequently derived using this map.
Figure 5 shows the method to train and evaluate FIC Sparse GPR to model the relationship between the log data and actual ground truth. Firstly, the geodetic from dataset were converted to north-east-down, also known as NED coordinate. The Sparse GPR for x-axis positioning was trained using log x is point with the x is ground truth. The same method can be applied for the y-axis for y-north point with the y-north ground truth. Then, the model was trained using 300 inducing points from a total of 843 x-east and y-north point log. As we can see here, the best fitted model selection is choosing the lowest of MSE and BIC value. And lastly, each dataset will produce the residual analysis and the performance of positioning error. Okay, we move on to data analysis. The GPR was trained using 5 types of covariant function, namely exponential, square exponential, method 3/2, method 5/2, and lastly, rational quadratic. The best performing covariant function is identified based on Bayesian information criterion, also known as BIC, and mean square error, also known as MSE, value that were obtained as the average from tenfold cross validation. The sparse GPR model with the best performance covariant function is then utilized to predict the improved trajectory point for each dataset. The MAE and RMSE in the positioning error after applying the GPR were compared to positioning error before the model implementation to observe improvement in position error. Autocorrelation ACF, partial correlation PACF, histogram, and quantile QQ plot conducted on the residual of X-East and Y-North model for each dataset were evaluated.
Okay, next we proceed to the result and discussion. The best kernel function for each GPR model that described the perspective axis positioning was identified based on the lowest value of BIC, MSE, and lastly, training time.
Table 1 explains on the kernel performance of X and Y axis of data set 1. The bold font is indicate the lowest value for each covariant function. and the red font is indicate the chosen covariant function. For MSE of x-axis is 0.0768. The MSE y-axis is 0.0890. The BIC value for x-axis is 2940 and BIC value for y-axis is 2200. Therefore, square exponential was identified for x-axis and MAT52 was identified for y-axis. Even though rational quadratic has same value MSE and BIC, the training time between square exponential and rational quadratic has a big difference. So, square exponential has been chosen for the covariant function.
Next, we move to the table 2, show data set 2. As we can see, square exponential, method 52, and rational quadratic has the same value of BIC for x-axis. Meanwhile, square exponential and rational quadratic has the same value of BIC for y-axis. Therefore, square exponential has been chosen for the best kernel function because the value of MSE for x-axis and y-axis has the lowest compared to other kernel function. Table 3 shows the data set 3. As we can see, square exponential, method 52, and rational quadratic has the same value of BIC of x-axis and y-axis. Square exponential has been chosen for the best kernel function because the value of MSE for x-axis has the lowest value compared to the others. Meanwhile, for method 52 has chosen for the y-axis because has the lower value compared to the others.
Therefore, from table 1 to table 3, square exponential and method 52 has been chosen for the best covariant function for each data set. Figure 6 shows the corrected noise present for each data set. As we can see, the lag is exceeding the upper and lower bound for autocorrelation and partial correlation. Figure 7 shows the histogram and QQ plot for data set 1. The histogram of residual x-east and y-north is skew distribution. Meanwhile, the QQ plot for residual x-east and y-north is not normally distributed.
Next, we move to the figure 8. Show a partial closed view of ground truth trajectory and the predicted trajectory point of data set 1 from GPR. The predicted trajectory is close to the expected ground truth trajectory, which confirms the improvement in accuracy of positioning.
And lastly, for the conclusion, square exponential and method 52 kernel produce the most optimized sparse GPR model. The improvement of positioning error produced by the GPR model ranged from 9.93% to 34.91% compared to the original measurement. The correlated noise was not eliminated in the prediction produced by the GPR model and revealed poor model fit as revealed in the histogram and QQ plot. To achieve a better model fit and to eliminate correlated noise in the residual, further optimization was needed in the sparse GPR model that described the trajectory data. That's all for me. Thank you for listening and see you.